Welcome to the Greek ship corrosion channel. My name is احتشام زاده. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 6. Thermodynamics of electrochemistry. The effect of soluble complexing agents on the corrosion behavior of metals. Here is the reference. Complexing agents are soluble species that combine with metal ions in solution to form soluble complexes, thus reducing the effective concentration of metal ions to extremely low values. This effect causes the electrode potential to move in the negative direction. Half-cell potential is decreased and increases the susceptibility to corrosion. According to the Nernst equation for a metal ion half-cell, for Mn plus M electron equals M, E prime equals E0 plus RT over MF ln of Mn plus activity. This dependency is illustrated in this figure. E0 standard half-cell potential, E prime half-cell potential under non-standard condition, R universal gas constant, T the absolute temperature, and the number of moles of electrons transferred per unit of the reaction, F the Faraday constant. Complexing agents are both inorganic and organic chemical species and may be found in many chemical process solutions. Naturally occurring complexing agents are frequently found in foods and may alter the predicted corrosion behavior of metal food containers. The example to be considered is the analysis of the tendency for copper to corrode in a deaerated solution of pH 8 with no complexing agents as compared to the corrosion tendency if cyanide ions are added to the same solution. It may be assumed that cupric activity equals 10 to the negative power of 4 equals molality of cupric ions, and that if corrosion occurs, the cathodic reaction is the release of hydrogen gas at 1 atmosphere pressure. Solution is deaerated. Cell representation in a deaerated solution of pH 8 with no complexing agent is Cu2 plus cupric molality equals 10 to the negative power of 4 and H plus pH equals 8 and H2 at 1 atmosphere pressure on Cu. E prime equals 342 plus 59 over 2 logarithm of 10 to the negative power of 4 equals 224 millivolts versus SHE. E prime for RHE equals negative 59 pH equals negative 472 millivolts versus SHE. E cell equals E prime RHE minus E prime LHE equals negative 696 millivolts versus SHE. Delta G reaction equals negative NF E cell equals negative 2 the Faraday constant times negative 696, that is greater than 0. Therefore, copper does not corrode with the evolution of hydrogen at pH 8. Potassium cyanide is now added to the solution. Cyanide anion activity equals 0.5. Cyanide anion complexes Cuprous to CuCN2-. The equilibrium constant K is the complex activity over the product of the activities of the Cuprous cation and the cyanide anion. Each one is raised to the power of its stoichiometric coefficient. Cu plus 2Cn minus equals CuCN2-. K equals 10 to the power of 16. It should be noted that the complex is formed with cuprous ions Cu plus and not cupric ions Cu2 plus cation. Since cupric cation is usually considered to be the corrosion product of copper, it is necessary to calculate the relationship of these two cations in solution. This calculation can be done from electrode potential data. Cu equals Cu2 plus 2 electron. E prime equals E0 plus 59 over 2 logarithm of cupric activity. Cu plus equals Cu2 plus electron. E prime equals E0 plus 59 logarithm of the activity of the cupric cation over the activity of the cuprous cation. E0 Cu2 plus equals positive 342 millivolts versus SHE. E0 Cu plus Cu2 plus equals positive 153 millivolts versus SHE. Consider a cell made up of these two electrodes with the cell at equilibrium, that is E cell equals 0. Then E prime Cu2 plus equals E prime Cu plus Cu2 plus 342 plus 29.5 logarithm of the cupric activity equals 153 plus 59 logarithm of the cupric activity over the cuprous activity. Solving for the cuprous activity. The cuprous activity equals 6.3 times 10 to the negative power of 4 times square root of the cupric activity, and still taking the cupric activity equals 10 to the negative power of 4 results in the cuprous activity equals 6.3 times 10 to the negative power of 4 times square root of 10 to the negative power of 4 equals 6.3 times 10 to the negative power of 6. With cyanide anion present, the cuprous activity is further reduced. Also, the activity of the complex ion will be the initial activity of the cuprous cation less the existing cuprous activity. The complex activity equals 6.3 times 10 to the negative power of 6 minus the cuprous activity. Since the amount of cyanide anion consumed is negligibly small, less than 10 to the negative power of 4, cyanide anion activity is almost equal to 0.5. Substituting into the following equation and solving for cuprous activity yields K equals the complex activity over the cuprous activity times the cyanide anion activity to the power of 2 equals 10 to the power of 16 equals 6.3 times 10 to the negative power of 6 minus the cuprous activity over the cuprous activity times 0.5 to the power of 2. The cuprous activity equals 2.5 times 10 to the negative power of 21. Equation in the previous slide is now used to determine the cupric activity with cyanide anion present. Cuprous activity equals 6.3 times 10 to the negative power of 4 times the square root of the cupric activity. Yields the cupric activity equals 1.6 times 10 to the negative power of 35. In order to reach the very low equilibrium concentration of cupric activity required in the presence of cyanide anion, a combination of the following reactions occurs. Cu plus Cu2 plus yields 2 Cu plus until the cupric activity goes from 10 to the negative power of 4 to 1.6 times 10 to the negative power of 35. During this process, metallic copper is being corroded. Cu equals Cu2 plus 2 electrons, Cu plus equals Cu2 plus electron yields Cu plus Cu2 plus equals 2 Cu plus. The net result is that virtually all of the Cu2 plus cation is taken out of solution. With the cyanide anion present, the copper half cell potential is now given by the following slide. The cell under consideration is now Cu2 plus the cupric activity equals 1.6 times 10 to the negative power of 35, and the proton activity at pH 8 when hydrogen gas is evaluated on Cu. E prime Cu2 plus equals 342 plus 29.5 logarithm of 1.6 times 10 to the negative power of 35. E prime Cu2 plus equals negative 684 millivolts versus SHE. E cell equals E prime RHE minus E prime LHE equals negative 59 times 8 minus negative 684 equals positive 212 millivolts versus SHE. Compare with the cell potential in the absence of complexing agent. E cell equals minus 696 millivolts versus SHE. The change in the Gibbs free energy is negative, and the reaction will occur spontaneously. Thus, the copper that could not corrode in the deaerated solution of pH 8 in the absence of cyanide anion now corrodes because the complexing of the cyanide anion to form CuCN2- has reduced the Cupric cation concentration to the extremely low value of 1.6 times 10 to the negative power of 35. Thank you for your time. Challenge number 9. If you like to challenge yourself, please answer this question in the comments down below. The complex ion could be looked upon as a chemical species in the solution to which the metal ion was attached at a lower energy than for attachment to water molecules. Can this concept lead to another interpretation for more corrosion of metals in the presence of complexing agents?